a taster of what this brings to geophysics and seismology, such that it would encourage you to go take a formal class in this topic if you realize that this is going to be of use to you. So this really is not meant to be a substitute for a class. But with that, let's get started. And so what is machine learning? This is technically defined as a branch of artificial intelligence, but one that is focused on learning structure specifically from data. So it's not based on symbolic reasoning or other types of AI decision-making. It's specifically focused on learning from data. It's been around for a long time. The origins date back to basically the 1960s. It has a lot of overlap with mathematical statistics, data mining, other fields, things like that. It has different names from where different algorithms were coming out of. So depending on if you were like electrical engineering and so forth, it's got different names like pattern recognition. But it's been around. However, you probably may have not even heard of it until relatively recently, I would say. And that's because in 2012, that is now being referred to as the year of the deep learning revolution. And so this in particular was a single talk in December of 2012 that triggered a massive revolution in this field. And so today, as a result, deep learning is now state of the art in many domains of artificial intelligence. So what does it mean to be in the middle of a revolution? It means that, well, if this is the number of papers that are being published per year, and the red curve is Moore's law, so that means that you're doubling every 2 years, machine learning papers are outpacing Moore's law. And so we are right in the heart of this thing right now, and it is not stopping anytime soon, I'm sure. So it's really just an incredible time, I think, and most people don't even know how much has changed since this started. So there's different flavors of this, and I'm going to go through both of them. The first I'm going to start with is what's called supervised learning, and this is all about learning a mapping function that is useful to you to do some kind of decision making. And so the idea is that, and I'm going to try to introduce you to some of the jargon that's in here. Machine learning in general is a very heavy jargon that's distinct from almost all the other areas of statistics, and it can make it hard to understand, but I'm going to try to introduce that to you. So the inputs in a supervised learning context are called features. Those could be d-dimensional, and you want to map those features into a set of targets or labels. Those are your predictions. You could make one prediction, you could make seed predictions. And the values could be of two forms. They could be discrete, in which case that would be a classification problem, or continuous, and that would be a regression problem. And so this is all about learning some kind of mapping function, f, that goes from these inputs to these outputs. And so just to give you a very simple example of this, so classification would be like this on the left-hand side, where you have two images, and the goal is to predict the dominant object category of the image. So here, you're classifying that into a set of 4 different types. Whereas on the right-hand side, you have a typical regression problem where you have continuous valued targets. That doesn't mean that the inputs have to be continuous. They could be categorical as well, or they could be categorical, but the targets are continuous valued, and you want to fit some function that can map these inputs into these outputs. Unsupervised learning is quite different. And this is all about learning some kind of useful representation of a data set. You don't have ground truth. You don't have Y that you want to predict. The whole point of unsupervised learning is to effectively reorganize a data set in some sense that it is useful to you. And useful is a very subjective term. It really depends on what you would like to do. And so an example of this might be something like this, where you have a collection of images of handwritten numbers, 0 to 9. And let's say you didn't know what those images were, but instead you wanted to somehow organize them such that similar digits were grouped together. And so if you had some kind of mathematical rules for how to organize things without knowing what the content was of this data set, you could do this such that you end up with all of the 6s grouped together over here and all the 0s grouped together over here. This is without a human ever labeling anything in this data set. So you want to learn some kind of useful representation of the data set that organizes things in a way that helps you. So those are kind of definitions for supervised and unsupervised learning. And we'll talk about both of those here today. So in supervised learning, the goal is that you want to learn a mapping F. And F is basically some kind of nonlinear parametric model that is designed to have sufficient expressiveness such that it can model basically any type of functional form that you want. And so F is learned directly from the data. How is it learned? It's designed to minimize the prediction error directly on an independent test data set. And I would advocate that this is really the hallmark of supervised learning. It is the fact that you have labels that are ground truth that you can set aside. You can set, so take some chunk of data, you put it aside, it's independent, you fit the model to the rest of it, and now you test that model on the independent data that has never seen the data before. And that's able to tell you how well the model actually performs. And this is very distinct from, a standard geophysical inverse problem where you don't have ground truth to do that. And so it makes it very difficult to tune, the fitting process. How do you control overfitting? All this other stuff. Here, you actually have ground truth set aside. And this, assuming you're not violating this independent assumption, that tells you exactly how well you're doing. So the trick here is that this requires ground truth labeled samples. And that means that ideally, a human has gone through the data set and individually labeled every single example there, such that you believe what the category is or the value is, whatever you're trying to predict, you have ground truth for that. And that's a key assumption here. And assuming that you have that, you can take a big data set and learn this mapping F. But it turns out that F is non-unique. It depends on many different things, and in particular, it depends on the model architecture, which is how you choose to parameterize this mapping function. It depends on something that I'll call a loss function, which is basically a definition of error of some form. It depends on how you choose to optimize this problem. And so for simple models, this loss function is convex, and that's relatively straightforward. But for most machine learning models, the loss function is highly non-convex. And it turns out that this is actually a major challenge to get the global optimum. And so that's a big part of this. And there's just many other things. And so together, the set of all these things, regularization, so forth, determines which mapping function that you end up with. And so I discussed briefly about architecture. So there's all different types of supervised machine learning models. The simplest starts off with the question. You want to mute? Thank you. The simplest of these is linear models. And so I'll get to these in a second. Neural networks is a really, really broad category, and this kind of underlies all of the modern advances in machine learning and what that's gotten us. Support vector machines is a relatively simple type of model that was very popular in the 90s, early 2000s, but has since fallen out of favor. And there's other types that are not kind of network-based. Ensemble models are based on graphs and trees. It basically uses nodes to make decisions and to learn stuff. K-nearest neighbors is basically assigning values to similar points or to similarly located points based on what values you've seen nearby and so forth. So there's lots of different types of things here. I'm just throwing these names out here. What I'm going to focus on today is neural networks because this is really kind of what the modern era of machine learning has to offer us. So what does this mean? Neural networks are layered systems that are designed, as I just mentioned before, to map some set of input features into a set of output predictions, some targets. And the way that this is done is in between the inputs and the outputs, you have something that's called a hidden layer. So this is your mapping function itself. And so if each of these nodes here is thought of as one distinct feature, what happens is this system is actually very simple. Mathematically, each node in this intermediate layer, this hidden layer, is associated with some kind of basis vector, and you are projecting this set of input features onto each basis vector, which is what these little lines connecting these circles tells you. So it's literally just dot products of these input features with some basis vector at each of these circles here. And what that does is it actually transforms your input features into your output prediction. And so that kind of assumes that you have very carefully chosen basis vectors here, which maps your inputs into your outputs. So how do you know that this is even possible in the first place? And it turns out that mathematicians have very carefully chosen this structure of this system such that it's very similar to something like a Fourier series, where it has been mathematically proven that for certain types of models, in particular one that has this series of dot products associated with it, followed by some kind of a nonlinear activation function, and I'll tell you what that is in a second, this system here can actually approximate any continuous function that effectively is bounded. There's some caveats associated with this. So they have proven this. And that means that you can approximate any function even without knowing what the actual form of that is, provided that you have input data and output data. That means that you can very carefully tune the basis vectors in this hidden layer to perform this nonlinear mapping in an optimal way. And so that means you can approximate this mapping function. Again, the mapping function is not required to be known. And these types of systems are excellent at classification and regression tasks. And so I'll give you an example of what this means. So let's take a seismology example, which would be local magnitude. And let's say that you don't remember what the form is for local magnitude, the functional form of that. But you remember what it's related to. It's related to amplitude at a station, the distance of a station from the source. And maybe there's some site correction factors or things like that. And you also have a big catalog of magnitudes. Someone out there has the equation and they've calculated magnitudes before. So you can take a big data set of these. And so under these circumstances, you can input these quantities here. You can make some predictions for magnitude. Initially, those predictions are going to be wrong because this model hasn't been trained. And so what happens is we can then set up a scheme to train this hidden layer by updating the parameters such that you minimize your prediction error. In this case, you bring your local magnitude prediction closer and closer to the ground truth. And so literally you are just updating the values of the basis vectors at each of these different nodes here. And you are just continually projecting these three values onto these different basis vectors. And so this would learn to approximate the ML equation without actually knowing what it is, which is very powerful, but also quite dangerous because you can learn functions that you don't know what they are. And so, so these types of systems require that the features, so in this case, your amplitude, your distance, and your station index are well engineered. And what that means is that they have to be very carefully chosen to be features that you think are very likely to help you predict the local magnitude. You can't just put in something that's arbitrary. And so what's an example of this? Well, what would happen if you tried to put in a raw waveform, for example, right? I could still collect my catalog of local magnitudes, but let's say rather than putting these three numbers here, amplitude, distance, and station index, I put in the elements of a time series, a waveform here. Well, it turns out that what that will do, number one, is it will significantly expand the number of parameters that are involved, because the size of these basis vectors is proportional to the number of input features here. And so that means that the number of parameters has gone up substantially. But it turns out that because what you are doing is continually projecting these inputs onto a static basis vector, it's not very good at recognizing patterns because it doesn't allow for any kind of offsets in time, in particular any kind of translation related things. So if you were to take a waveform and line up every one of the seismograms exactly at the right time step, you could do something like this potentially. But if the seismograms were not perfectly aligned, it would be a lot harder to do this, because all you're doing is a dot product between the input waveform and each of these different basis vectors. So these types of systems tend not to do well when you have translation related invariant properties in the data. And so that led to, in the late 90s, the development of a different type of network that is called a convolutional neural network. And these types of systems are designed to allow you to input raw images, or in our case, raw seismograms directly, without the need for extracting or engineering features beforehand. So you don't need to choose amplitude or distance or things like this. And you also don't need to very carefully line up all the seismograms, make sure that everything is just perfect. These systems are designed to be able to automatically extract their own features from the raw data. And the way that this works is, so let's look at this cartoon here where you have your input waveform. So in this case, it's 3 components. And you want to maybe output a set of class predictions. So in this case, maybe you want to classify this into the dominant signal category. So it being a P wave, S wave, or noise. The way that a convolutional neural network works is that it combines something that I'll call a learnable feature extraction system with the standard type of neural network like I just showed you before. And so what happens is, if this previous network is all about just dot products, so you are projecting, these 3 numbers onto a 3-number basis vector here, well, with a convolutional neural network, what happens is that instead of just a straight dot product, it becomes a convolution operation. And so you end up having a system that's composed of learnable filters. And so this kind of little thing here is supposed to represent a learnable filter, where the values of the filter, again, are learned from the data. And this filter gets convolved with this input time series. And that convolution operation produces basically a heat map that activates when it finds something that's looking for. And so convolutions, as we know, are basically just sliding dot products. So in that sense, it's an extension of what we saw on the previous slide. And so this is supposed to be some kind of representation of a heat map where this filter finds things that it's looking for. And what ends up happening here is that you have a stack of heat maps. Each one is supposed to represent different types of extracted features in this signal. And what's typically done is that you would then downsample these heat maps so that now you're looking at basically a different scale. And you would repeat this. So you have another set of filters like this that are learned, and each one, you basically just slide it along in a dot product sense. So it's a convolution or a correlation. And again, you produce another set of heat maps like this. And you just keep doing this over and over again. And what ends up happening is, after you've downsampled it many different times and you produce these stacks of heat maps, you end up extracting features that are independent of where they are located within the input seismograms. And so if there's features here like particle motion or things like that, that these filters are designed to look for, they can extract those patterns anywhere within the time series. And by doing this, you can then now take those extracted features, so you can now think of these as just basically learned features. they're equivalent to like this amplitude, this distance, and station index here. Hopefully the system's learned to extract these things on its own. You can then feed these now into this neural network like this and output your different class predictions accordingly. So that's kind of the idea behind this system. So it combines, again, this learnable feature extraction system where the learning is designed to minimize your prediction error given an input seismogram against the ground truth for what the actual class is. And so because they have this embedded convolution property built into them, it encodes the ability to have invariant pattern recognition. So the true invariance here is translation invariance, but they're also really good at detecting patterns. If you reflect it, if you distort it, rotate it, things like that, they tend to also do really well with those types of different mappings of patterns. And that's not the case for these standard fully connected networks because all you're doing is a straight dot product without allowing for any kind of invariant recognition. And that's why this is really a bigger advance in particular for our problem. So what's really powerful about these systems is that they're capable of generalizing the knowledge contained in very, very large data sets. So if you give me a data set that has 1 million different seismograms in it, I can train a single model such that it learns to classify these input seismograms into a set of output classes, regardless of which seismogram you're giving me. And so it's able to distill this massive amount of information that could have been collected over decades. And it's not necessary for you to match exactly something that you've seen before previously. It's able to learn and to generalize those major concepts. So yeah.
Zach, can I interrupt you for a question?
Sure, please.
So the question is there any main factor controlling the quality of the results, the predictability, more than the others? For example, the amount or quality of data, the number of features?
Yeah, so here, I would say that the data is probably the most important aspect about it. You need lots and lots of data. Here, you're talking about on the order of hundreds of thousands to potentially millions of ground truth labeled examples. That's the key. And you have to be confident in those. But there are many other factors that control the performance as well. And it's just hard to make kind of sweeping statements about what is going to affect what. I think a big part of modern machine learning is being aware of all of these different factors, how they contribute to performance. And it's really an iterative thing. You don't just start off and assume that you're going to train this one time and walk away. It's something that you have to work at, test lots of different things, see how it affects them, and use your intuition from potentially previous applications of this to help you make a decision accordingly.
Okay, that question asker said thank you, and I have 3 more questions before we move on. So the first is, can we control the patterns or features to be extracted? For example, if we care more about the travel time, can we design some basis that can extract that information?
Potentially, if you feel like this is something that's universal and is always represented in the data set, then you can encode knowledge of the physics and so forth in there potentially. But I would caution you because much of I would say that the major gains really here have come out from relaxing the idea that humans know best. And so if we go back to this example here, right, this is developed by Richter 100 years ago, who was looking at the data and realized that amplitude, distance, and some other factors were supposed to help you calculate this quantity. This is very, very carefully considered. However, many other problems are not necessarily the case, that we don't know perfectly like this. And this idea here has shown time and time again within the machine learning community that starting with the raw data and letting the system self-optimize to decide what it thinks is useful is where the advances have really come from. And I'll give you an example of this. In the 1980s, people were defining the values of these filters based on by expert judgment. They were not learned. And that was a major barrier within machine learning until they let this entire system become optimized. Because back in the 80s, computer scientists thought that they were the experts and that they knew what the best filters should be for these systems. And they forced them to be those values. And it turns out that letting the system self-optimize gives much better performance. So I would caution against relying on what you think is best, because unless it's absolute universal, it may not be the case.
Okay, I'm going to ask another question.
Mm-hmm.
The question is, since the input is raw data and you're wanting to classify the raw data with the assumption that you're going to eventually input real-time data, how do you deal with the fact that some signals will contain mixed, so basically how some waveforms will contain mixed signals within the same waveform?
How would you mix signals? So you're concerned about having different phases and things like that within the wave train?
That is my understanding of the question. We might pause for a second or two to see if I'm interpreting it incorrectly.
Yeah, in part, it's how you frame the problem. So in this case here, it would be that you would set the problem up such that maybe you assign a ground truth label to whatever you think is the dominant signal category within the window. It's a big part about how you choose to architect the problem itself. So it's not just that the inputs and the outputs are just taken as some universal values. You actually have control over how you've set up the problem. And I'll talk more about this in one slide.
Okay. So, and then kind of a follow-up to that answered the first part of their question. That says thank you. And a follow-up would be, is there a way to classify potentially rapid repeating events?
Yes, but that's a very specific question.
Okay, so maybe we'll put that on the back burner. And then, okay, we have a couple more that these might be kind of quick answers. So the first is that, will these models work regardless of underlying geology?
They, not universally, but they can do quite well generalizing to data sets that you haven't seen before.
Okay, and then two more quick questions. Do we get a chance to understand the physics behind the mapping at any point in this lecture?
No.
Okay, so maybe maybe Zach can provide some papers or references later on if people are interested. And then this is a point of clarification. What two things are being convolved together?
Okay, so at the simplest case, you would take the input waveforms, and so there is basically for the input layer here, it's a stack of filters, and the filters are actually very short. So they're on the order of maybe 5, 10 samples at most. And the filter is just convolved with this waveform here, just like you would with a standard seismology. It's just that the values of the filter itself are not a type of filter that we're used to thinking about. It's a filter that is where all the values are learned from the data, but otherwise it's no different.
Okay, thank you. I think that concludes our questions. So
yeah. So I want to stress that this type of system, the power of it is that it can take a huge data set. It can learn from and generalize all of that knowledge contained in it, right? It's not matching one seismogram against one prediction, such that you give it a brand new seismogram that you've never seen before, and it can say, well, here's all the things I've seen in the past. How did those look? And then use that information to make a prediction for this new signal. So it's not just straight up, template matching, for example. And okay, so we can take this a step further, right? Here in this previous slide here, I'm talking about making a single classification for an input seismogram. But let's say that I had more detailed knowledge. Let's take a photograph like this, and let's say that a human goes in and manually labels every single pixel and segments out different types of objects within that image, right? So here, this column is supposed to represent ground truth, where all these pink things are people. This is a plane, right? A train is colored green here. Every pixel here is a train pixel. So if you had pixel-wise labels somehow, which is obviously very difficult to obtain, turns out you can actually take this type of model and do a many-to-many prediction. So given an input set of waveforms, we can make a set of pixel-wise class predictions, and that's actually been done in seismology to great success. So for example, here you input a 3-component seismogram like this, and if you have ground truth labeling at every single time step here, rather than pixels, for the different types of classes, so P and S shown here, you can train one of these deep neural networks to duplicate this type of decision-making process. So it's segmenting out time steps that are basically concentrated around the phase arrivals. This has been very successful so far. It's really led to, vast improvements in what we could do even a few years ago. So, so this is quite promising. There's lots of other different applications of this that I just want to give you a taster of some of these things. You can do denoising of images. So if you somehow had an image that was clean, for example, you could input a noisy image like this or like this, and have this network map you into a cleaned up image like this. So it's a denoising type of neural network. It's pretty remarkable. And this paper here is just recent, right? Only a few months ago. So this is a very current and active topic within machine learning, as you can see, because this image here, the results here were from like a standard type of network that I just showed you right here. So this is like the old school type of thing at this point. And this is what you can get with state of the art, which is obviously much better. So, so this is kind of a neat application here. And I'm going to give you a tour through all different types of other things as well, just to kind of stimulate interest in this subject. So we can also talk about data sets that are sequential in nature. So in seismology and geophysics, we're often dealing with this kind of thing where a sequence could be, time series. Every time step, you have some values. It could be our waveforms. It could be, earthquakes at each time step or so forth with variable time stepping, things like that. Lots of our physical data sets have this structure to it, multivariate time series. And there's types of networks that are designed to work on sequences. And what they do is they simply process each element of a sequence sequentially. And so if X is representing different elements of a sequence and their features at each time step, you simply would input this to a network. It's going to look at the features here and make some predictions and use the information from the previous time step to make a better prediction for the next time step and so forth. So there's networks that are designed to work with sequentially structured data. And it doesn't have to just be time. It could be also just context and positioning. So for example, if you have words in a sentence, right? And the classic example of this is like if you want to do word prediction, if you pull a word out of the middle of a sentence, you want to predict what's in there. Well, you would want to make a prediction conditional on the previous words, as well as maybe some words in the future. And so you can have a model that's going to look at each word separately, together with some information that's passed along as you process each word. And it's going to map your set of words into a prediction for the missing word. And this has been shown to achieve very outstanding performance within machine learning. So for example, when you talk to, Siri or Alexa or any of these things, right? You have to go through a process by mapping speech into text. So it records your speech, and then there's actually a neural net underneath it that decodes this into a a vector of words, essentially. It's an integer coded vector of words that it then uses to make decisions on. So that's how these systems are able to understand what it is that you're saying. They can also go the other way around, and they can synthesize speech from text. So you input a set of words coded as integer coded in a vector form, and it actually produces an output waveform that's audible speech. So all this stuff today is done with artificial intelligence. They're also excellent at language translation. And so if you were to input a sentence in one language, it's able to actually translate this sentence into some kind of latent representation of the sentence, some kind of intermediate product, and then decode that latent representation into the target language that you care about. And so it's processing each character in the sentence sequentially. It's keeping track of context along the way and using that context to better understand how to do this translation. So if you go to Google Translate right now, it's substantially better than it was even a handful of years ago, because now they've switched over entirely to using AI-based translation algorithms. And if you were looking at this stuff even 10 years ago, it basically used to use rules that would map like one word into another word, and you would end up with these broken sentences that didn't really make any sense. And today, all the language translation stuff is just outstanding. So all these advances have come from the use of these types of networks in modern day life. There's other really cool stuff going on. We can also talk about accelerating compute capabilities. Here's a paper that we just put out a couple months ago, which is solving PDEs. And in particular, this is doing seismic ray tracing, where these are different velocity models here. The left column in each case is a finite difference wave propagate or ray tracing solution. And then the central one is using a neural network to solve the Eikonal equation. And it's literally trying to predict the velocity at each point, or really a travel time field, such that if you take the gradient of it, it gives you the velocity. And so you can see these contours here between these different cases and see that compared with the finite difference, that these neural networks are actually doing very, very well. And it turns out that this is much faster than solving this with finite differences. There's lots of other really cool advantages that come with this. So it's not just about, you know, working straight up with data. There's going to be big advantages for solving PDEs, accelerating compute capabilities, things like that for us going forward. And I don't really have the time to go into this in detail, but I just want to kind of throw that out there as it's not only data type of argument. Okay, so all of these algorithms that I've talked about so far they fall under the realm of supervised learning. But there's also a branch of machine learning that's called unsupervised learning that we discussed very briefly. And again, I'll define this by trying to learn some useful representation of the data, learning some distribution of the data, something like that. And to give you an example of this, 4 years ago, there was a paper that was published, or if not 4 years, in 2014, on the topic of generative adversarial networks. And this has led to basically what people view as the single biggest advance in artificial intelligence in at least the last decade. And so to give you an idea of how powerful this is, what it does, if you look at these photographs here, if you look very, very carefully, you can see how beautiful these photographs are. Every single one of these people does not exist, okay? Every one of these is a computer-generated photograph. None of these people are real people. They're fully computer-generated, where the rules for this have been entirely learned from a large data set of photographs. And the idea for this is that if you have this big data set of images, you want to learn a model that captures the distribution of all of those images such that any one of the real images could be drawn from that probability distribution. And if you have learned that distribution, that then gives you the ability to sample from it. And so here, every single one of these images has started out as originally a vector of white noise, literally white noise. And you can just do this forever. You can just keep generating white noise vectors, and it maps those vectors into a real looking photograph. And so what defines real? Well, it turns out that the definition is based on whether a neural network can distinguish between whether it's real or fake. And so you end up tuning a second model that generates these images such that another neural network can't tell. And so it's basically this kind of adversarial training where one network generates the images, the other one decides whether images are real or fake, and they trade off with each other until eventually the generator is so good that the discriminator can't tell. And you end up with something like this, which is incredible. Because most of these, I think humans would not be able to tell that these are not real people. And so you can take this a step further. This is already old. This is 4 years old. You can take this very, very recent paper that came out only a couple of months ago. And this is something called a style GAN, or generative adversarial network, that you input some original image like this, and you can condition an output image on the style of another image, another person. And so you can do this mapping, right? There's no ground truth that you could ever have to learn this mapping into this one, right? This does not exist. These are computer generated images. And that's what makes this fully unsupervised, because there is no ground truth. You are simply learning distributions of the data that are useful. And in this case, useful means something that is conditioned on the style of another image. And this is it's just bizarre. You can do, if you look online, there's all sorts of things like mapping photographs into Van Gogh style paintings, you know, changing the seasons of photographs from one to another, things like that. And so there's starting to be work within seismology that is using this type of technology to simulate things, simulate wave fields and so forth. And it's incredibly powerful, because here you have some kind of mapping function that you don't even really know how to write this down in any kind of closed form. We don't have a clue, but somehow the system is able to learn how to do this. So this is pretty neat. So I've kind of toured through all these different types of models here. There's many different types of supervised models, lots of unsupervised models. And again, the goal of this today is not to teach you machine learning. It's to give you a taste for everything here so that you are encouraged to take a real class on this. But I want to give you some sense of what goes into all this, right? How do you even choose what algorithm to use? All this stuff depends on many things. It depends on the mathematical structure of the data. Knowing this well, you're the expert at this stuff. So you need to know the ins and outs of the data structure. You need to have lots of data available. Depending on how much you have would determine which algorithm you might use. Maybe you don't have that much at all, and so maybe a deep neural net is not appropriate for you. It depends on how good your ground truth is. If you're not all that confident in your ground truth, maybe you need to use a different type of algorithm that can essentially capture the error appropriately. Maybe computational demands are important to you. If you want to do something in a real-time context on a cheap, you know, sensor of some kind, maybe you don't have state-of-the-art GPUs to do the calculations. So you need to use something that's relatively lightweight. So there's lots of different factors. Also, maybe the interpretability of the features is important to you. So there was a question before about black box stuff. There's some ways to kind of work around this. Certain types of networks allow you to assess feature importance, but it's not, I would say, very satisfactory. You don't really get a whole lot of insight into these currently. I would tell you that state-of-the-art models are not often the most practical, right? Some of these require 100 million labeled examples, which you probably don't have. So maybe you don't want to start off by trying to pull a network from, you know, the machine learning conference that happened 2 months ago, right? So you want to often start simple and show that you progressively need a more sophisticated model to get better and better performance. And maybe that performance is marginal, right? What matters to a computer scientist is not necessarily what matters to an earth scientist. But my point in all this is that it requires knowledge of all these different types of algorithms. And in general, most of this comes down to being experience-based. And you build this by working on different problems and trying things and seeing what works, what doesn't. So it's really hard to just say, like, people come to me, what should I use, and so forth. You got to just try this on lots of cases, get your hands dirty, and slowly build up intuition for this kind of thing. So all of this stuff has been about describing models, how they work and so forth, but we didn't really talk at all about training. And so in machine learning, we distinguish, first of all, between something called parameters and hyperparameters. Parameters, they characterize the mapping function itself. So these are learned from the data. Hyperparameters, they affect model performance. They're not necessarily learned. And so these could be parameters that you tune as part of the optimization process. And then once you've optimized the model, well, they just go away. And so, they could be also how you compose your architecture of the model. So if it's a layered system, that could be the number of layers, the number of parameters in each layer. If you have regularization, how strong to use that, things like that. Those are all called hyperparameters in the machine learning jargon. And so training a machine learning model is therefore the process by which the parameters of this mapping function are learned. And the modern kind of deep learning is all about training with something that is called stochastic gradient descent. And this is based on taking a really large data set, cutting it into small pieces, and iteratively fitting the model to these pieces rather than fitting one model to the whole data set simultaneously. And the pieces are chosen randomly, for example. And it turns out that because deep neural nets have a non-convex objective function, that this type of optimization algorithm is very effective for training these things very efficiently. What I didn't talk about is that also the elements of these neural networks are very carefully chosen. They're all, linear transformations followed by, nonlinear functions. And those have all been carefully chosen such that they are analytically differentiable. And so what that means is when you do this gradient descent, you can actually write down the analytic expressions for these gradients to do the optimization rather than doing it with finite differences. And so that makes this quite appealing to use for training. And so training involves iteratively updating the parameters to minimize the prediction error of these models directly against the ground truth. And so, as I mentioned before, we always measure the performance on out of sample test data or validation data. And that's because we have this available to us, right? We can set this chunk of data aside. We can fit the model to the rest of it and then test how well the model performs on this data it hasn't seen before. And that's the key to this whole thing. You know exactly how well it does, assuming that you are using the same data distribution for the test and train sets. So people always come to me and they say, well, how much data do I need? And I can't tell you this because it's very problem specific, it's model specific, it's algorithm specific. And so, if you really wanted to push me, I would say that you probably want to aim for something like 10 times as much data as the number of model parameters in order to have no overfitting. However, the problem is that deep neural networks have something like 10 to the 6 to 10 to the 7 parameters, right? So millions to tens of millions. Actually, I just saw, a paper maybe a few weeks ago that has like 2 billion parameters in it, right? And they don't have anywhere near 2 billion data points that go into this. And somehow this is still state of the art over a model that has millions of parameters. And so what this has really shown time and time again is that even though people have these rules for how much data that you want, often pushing these models much deeper still tends to end up giving you much better performance if you don't meet the data requirements than having like a shallow network with very few parameters. And this is also something that computer scientists don't really understand very well today. It's still kind of mysterious and not theoretically well justified.
Hey, Zach, we have a question about overfitting.
Sure.
So, and you mentioned this is certain criterion for amount of data you want to have.
Mm-hmm.
Are there other sort of ways to avoid overfitting the model? Is the question.
Yeah, the key, for some reason this got deleted here at the bottom, but the ways to deal with overfitting, if you know you have it and you can increase the data, so it's not a viable option, you can add penalties to the objective function, so regularization. So it's effectively smoothing. The difference between this and like a standard slip inversion or geophysical inverse problem is that you have this independent validation set, so you know exactly how to tell whether you've added too much or too little regularization. You just test it on your validation set, and once it maximizes the performance, you're done. So that's one way to do it. There are other techniques called dropout, for example, which randomly drops out pathways which within these neural networks during train time. And the idea is to force the network to learn to use different connections and things like that, which effectively amounts to a regularization strategy. So there's that. There's just lots of different things that people have tried to do this. But the good thing is that you have a mechanism for assessing how much you are overfitting, whereas in standard geophysics stuff, we don't know that. It's entirely subjective. Or you use some kind of heuristic to guide the choices. Other questions?
Yes, I think so.
Mm-hmm.
Someone asks, have people applied machine learning to earthquake forecasts?
Right now, there is very limited amounts of work that have been done on the topic of earthquake forecasting. There's some work that's done on attempts to spatially forecast. In all of these circumstances, the conclusion so far is that there really hasn't been anything significantly improved beyond what existing types of like non-machine learning models can do, I think. There's a whole paper that was just published not that long ago that looks at like 20 or 30 years of trying to use neural networks to forecast seismicity and concludes that there really isn't anything statistically significant there.
Okay, so this might relate into the next question, which is, have you applied this technique for earthquake localization?
For earthquake localization, so hypocenter inversion, I guess. We'll go with that. The answer is yes. Yes, we have been doing this extensively. This is one of the areas where it has been really a major advance within seismology, because these types of networks are excellent at detecting phases, picking the onset times, things like that. They are orders of magnitude better than previous generations of algorithms and come very close to duplicating what humans can do, and in many cases can go beyond that. So that has been a big improvement.
Mm-hmm. Good. And then the last question, as it needs a massive volume of data, is it only applicable for overdetermined problems?
Well, no, because as I just mentioned, like some of these, so the modern language translation models will have billions of parameters in them, and they do not have anywhere close to that much data going into these things. So there is something fairly remarkable about the properties of these networks to be resilient to overfitting, right? When we talk about slip inversions, we're talking about like 1,000 parameters, and we're worried about being able to fit anything. And here I'm telling you about a model that has 1 billion parameters in it. And that can still do better than a model that has 1 million parameters on the same data set. So, so there is this innate ability for deep neural networks to be just resilient to overfitting in a way that we would not expect from like all of our standard training about data science. And so I would tell you not to worry if you don't meet like these rules of thumb, because they really seem not to apply. These rules of thumb were often, I think, kind of predate the modern advances in machine learning.
I was curious about feature engineering and with the convolutional neural network, how those features are learned essentially. I was wondering if you could take that part of the CNN framework for feature engineering,
Yeah.
you get your significant features and then apply it to other methods, right? Like apply it to SVM, for example, or something maybe more simple on that side. Like how do you, what's the best way to go about, extracting these significant features from the data?
Well, so you can pop off the deeper layers of the network once it's trained, and you can output those extracted features. The real issue is that it's not necessarily in a form that would be of use to you. It may be in a form that the machine knows how to deal with very well, right? And so that kind of gets to this whole thing of, what humans think is useful versus what, these algorithms think is useful. They're not necessarily the same. It doesn't mean that you can't get some insight into these, but it's so. Yeah, it's hard to say this, especially in very general terms, right? For something that just holds for any problem. I think if you were to study a specific problem very carefully, you might be able to draw some kind of meaningful conclusions about the learned features. In particular, I think for the image recognition community, they've done this, right? And so they end up with, so just to give you kind of a sense for this, the filters for the image recognition ones end up having pieces of, like, if you train it on faces, for example, the filters at different layers of the network will learn, they'll learn kind of hierarchical feature extraction, so that like the shallowest layers will learn essentially detect edges at a very coarse level within the image. And then as you get deeper and deeper, you start extracting like very fine scale features, so eyes and things like that. And they learn this on their own. It's just kind of the way that the layered structure is set up. And so you can look at the filters and see what those look like. You can also pick a single filter and then search for an image that would have maximized the activation of that filter, what that would look like, to give you a sense for what the filter is looking for. So there's different ways to kind of assess what these systems are learning and they're extracting, but it's very problem dependent, and it's just a hard thing to do. Any other questions? Okay, and just to kind of wrap this up, what if you don't have any ground truth or much, right? There's other ways to deal with this stuff. So I don't want to discourage people. They say, I don't have 1 million seismograms to do something. There's something that we call sim to real, which is basically if you have a model that you trust, you can synthesize training data from that, train the model with the synthetic data, and then apply the model as is to the real data. And we've done this, and it's worked quite well in our case. So we did this for a type of earthquake detection problem, looking at different waves propagating across a network and linking together detections of different sensors. And we trained the thing entirely with synthetic data, where we just put random earthquakes in different parts of our study area and just build a training data set accordingly. So this sim to real approach can be effective, but the key is that you have to have a model that you trust. And that's because neural networks tend to do weird things when the distribution of the data that you train on is very different from the distribution of the data that you apply the model to. So that's one thing. Another thing that you can do is something called transfer learning, where you basically train a model on a surrogate data set where you have a lot of data. You use that to learn coarse structure in the network, and you can then retrain the model now on a limited data set that you really want to apply it to. So Let's say, you have a lot of data in California because we have a big network here, but you want to apply your model to, somewhere else that you've put out a new network that never collected data before. Well, you could train your model on our Southern California data, take the parameters, and then use those, for example, as the starting point for a new training process on your limited amount of local data, and it'll adjust the model in a fine-tuning sense to that new data set with, relatively small amounts. And you could get away with using like 1,000 examples. And so the idea is that you're kind of just fine-tuning the pieces of it so that it learns to slightly adapt to the differences in the data distribution. So this is called transfer learning. I think it's going to be a big part of our business going forward. It's very powerful, and we've already seen some really good success with it. And so kind of, the end is, why did this all happen recently? 2012, I told you, December, there was a big revolution from a single presentation. And it really all comes down to, in part, this thing called ImageNet, which was basically a database where that was set up, where they crowdsourced image labeling. And in particular, 14 million images were crowdsourced. So they put out a bunch of images, they sent them out to people, and they said, just label this for us. And they built this big data set. And before this happened, they didn't really have a large training data set to use. And so the development of this kind of universal data set that people could use to train models just completely transformed things. And it led to competitions, for example, where they had this image recognition contest. This is looking at the error rate versus the year of the competition. And you could see that the error rates went down and down and down until 2016, when they basically were flattening out at a rate of almost 0. And then they shut the competition down the next year because they felt like there wasn't going to be any more improvement on this challenge. So having this big data set available together with challenges like this really pushed the community to just dramatically improve what they were able to do in a very short period of time. And so I think that's pretty exciting. So to summarize, machine learning is a rapidly growing field. I can't possibly do this all in one lecture, and I have not tried to, hopefully. So if you found this interesting, I recommend that you take a formal class on this. There's just lots of stuff that you need to know, the do's and don'ts of it. This doesn't mean like you just go home and immediately start training up a model and doing it in your research, because you're probably going to be making choices that are suboptimal. It really needs a lot of care and broad appreciation for all the different algorithms and things out there. It's led to major advances in all areas of science and technology at this point, and everything from medicine to chemistry to so forth, to seismology. It provides tools for automation, which I've mostly talked about here. There's a lot of promise for accelerating compute capabilities, which I think is very exciting, PDEs and things like that. But then there's also tools for data discovery, and so that's going to be very important for us too. So I think this is going to be a big part of just general geophysics research going forward. And I'm happy to take questions before we move into the hands-on stuff.
I was curious with your last slide, ImageNet, like whenever I have to select all the crosswalks in this image or something, like is that data being used for something like this?
Yes, it is. It's exactly what it's doing. Yeah, so that is one of the issues. So a lot of the different tasks in, I don't know how to call it AI, but just different areas of tech and whatever, they don't have the data to do what they want to do. So they are constantly trying to find creative ways to get access to those types of data sets. Crowdsourcing is a great way to do it. Seismology, we happen to be pretty rich in a lot of data, right? So earthquake seismology, we've got millions and millions of labeled examples across all the different seismic networks globally, going back decades. So we have lots of this stuff available to us already for certain types of problems. But for other problems, yeah, you might need to either be creative, crowdsource it, You could do Amazon Mechanical Turk and put up a bunch of unlabeled things and have some random people online go and label them for you. Yeah, but these are all just attempts to get good data sets.
Could you comment on what the biggest pitfalls tend to be in the seismology community in applying machine learning? Like, what are the biggest mistakes that people tend to make?
I can talk about some of them. I don't know if I would single out specific ones, but a lot of them are violating basic assumptions about these models. And these networks are designed to be applied directly to the data that you train it on, as is. If you change the data distribution, even slightly, they can do erratic things. And it's not just like a linear, error. It could be something that is completely crazy. So, so people will commonly take data sets, train on one, apply it to something different, and assume that it is going to generalize perfectly to these other data sets. That's not necessarily going to hold. So, and how much it does not hold really depends on the problem, how far you move away from the original data distribution, things like that. So that's a hard one, but there's lots of assumptions that go into these networks that people should be aware of. And that's the kind of thing that a formal class will teach you all about, so that you are, clearly understanding of the implications of these things. Other things that people do. So other things that I have seen, for example, are applying pre-processing to training and validation data sets, for example, that is not the same, and it can bias the outcomes, or it could give away the answer in some cases. So how you apply the pre-processing has to be done in a way that the neural net cannot find out the answer identically just by looking at the pre-processing you applied. So for example, let's say you have you have a data set of earthquake seismograms, right? And you have different magnitudes, and we know that magnitudes control frequency content, things like that. So maybe you thought it would be smart to apply different filters to the large events and the small events, and then use that to predict something, okay? The problem is that then you have injected a bias into the data set that is not uniform. And therefore, it could learn to recognize the filter and correctly predict the answer every time without actually learning anything useful. And that wouldn't generalize to anything in the future because you wouldn't have that filter, accordingly. Like, let's say you wanted to calculate the magnitude, right? If you didn't know the magnitude beforehand, you couldn't apply the right filter, the right band. So people do that kind of stuff. There's just all sorts of things like this that I will see in reviewing papers and so forth. But again, this comes from like a formal class, having a lot of experience hands-on applying these types of models, making a lot of bad mistakes. And I've done this, had some amazing performance that I realized later that was not real. And yeah, just collectively working hard at this for a while.
Okay, we've got a handful of questions to maybe end this lecture out. So the first is it possible to constrain the model parameters being sparse rather than being smooth, having a long-tailed probability distribution?
You can add, you can constrain them to be sparse. The question is, why do you want model parameters to be sparse? Right, so it turns out that in a neural network, the model parameters are not physical. They are, the parameters that control the mapping function from X to Y. And so unless you have a reason to believe that that mapping function should be sparse, it is not the same thing as saying, like, you know, you think a slip inversion should be sparse, because that's physical, right? So yes, you can do this, but you would need a motivation for it. You could just want to straight up regularize it, but then at that point, it's probably not really any different from, you know, an L2 regularization versus an L1, other than like whatever performance benefits might come from it. But you have to think about, in these supervised learning models, you're learning the mapping function, not the model parameters, the physical model parameters.
Okay. Oh man, we're getting a lot of questions. So how fast will the fine tuning of a neural network trained along with another data distribution, or is it worth retraining from zero?
I'm trying to guess at what this question is. So is the question, how long does it take to do the fine tuning, so this transfer learning approach, compared with training the model from scratch?
Yeah,
Yeah, I think so.
yes.
Okay, so the transfer learning could be rapid. You know, you could do that on a tiny fraction of the original data set. So it could be, I mean, it depends strongly on the hardware that you're using and so forth, and the architecture, but it would be orders of magnitude faster than training it from scratch.
Okay. So I'm just going to keep shooting through these questions. Is it difficult to obtain models that generalize well in seismological applications?
Well, I mean, seismological applications is fairly broad by my definition. I would say that at least within like the earthquake monitoring discipline, it's quite easy to obtain models that generalize well. You know, we've applied this stuff to Japan, trained in Southern California. People have done it in Oklahoma and all over the place. I mean, we've applied our models trained in Southern California to geothermal data sets at boreholes of several kilometers at kilohertz sampling rate. I mean, all sorts of stuff. So in many ways, these models have worked well on situations that I would never have expected them to. And then in other ways, they can break down. So it's just hard to say, but we have kind of, you know, backup strategies in place to deal with these types of things. We use multiple sensors and that kind of thing to ensure that the results are reliable.
Okay, so we have 3 questions, and then I think we maybe will wrap up questions and move on to the lab section.
Yeah.
The first is, would you mind elaborating on the computational cost according to the network architecture? And maybe talk a little bit about the computational resources you require for your research. Oh, this is probably actually a really great introduction to.
Yeah. So the computational resources for this stuff are generally huge. If you're doing any kind of deep architecture, you pretty much can't do it without GPUs. And that was also one of the key things. In 2012, the paper that kind of revolutionized all this stuff was the first to demonstrate that GPUs could be used to train all this stuff. And before then, they didn't have the kind of resources available to do this efficiently. And that's because it turns out that the training problem is massively parallelized. GPUs are hardware that's designed to do massively parallel floating point arithmetic. So they're very efficient for doing the training. And so you need big resources. The demo I'm going to show right now will use basically state-of-the-art GPUs to do the calculations. And then we will split off into groups, and you will run some stuff on your own that does not use GPUs. And so the models are kind of like classical models so that everybody can be ensured that it works for them. But you will be able to compare the results of those classical models to the one that I run with the GPU. Okay.
Yeah, I think, can we just do, let's do 2 more questions, hopefully really quickly, and then move into the, I just want to make sure everyone gets their questions answered. So these, I think, might be fast. So can networks learn to output the probability density function on Jacobian derivatives of the mapping function, given that we do not have derivative information during network training?
I'm not entirely sure I know what you're referring to, but that's a bit of a specific question here.
Maybe that.
I'll just say that the neural networks, as I mentioned before, are special because all of the pieces of them are analytically differentiable, assuming that you choose your activation functions appropriately. And so you can just write down the equations for an n-layer deep network on paper. And those gradients are guaranteed to be differentiable like that. So that property has been exploited by machine learning researchers to do all this training efficiently, but also by many people like myself for, in our case, solving PDEs, where we take the gradients of the PDE analytically. And so it's the true derivative at that exact point, not a finite difference at that point. So that's just some general comments about the differentiability of these systems.
Okay, and then this will be the last question. Hopefully this is quick. Why is solving of a PDE faster with machine learning than with finite difference?
Excellent question. And that's because finite difference scales with the number of simulations that you need to do. And so in our case, you can think of this as if you had an earthquake source at one point and you wanted to do ray tracing, you solve the ray tracing equation, right, the O'Connell equation. And then if you want to shift that source epsilon to the right, what do? Well, you start the simulation over again. Turns out with neural nets, they can actually use the context from the previous simulation as a starting point and update that to this epsilon shift, which allows you to generalize much better. So it doesn't need to start from scratch for every single simulation, and it can rapidly converge to a much broader range of scenarios. And so in our case, we actually trained this model to solve the O'Connell equation for all sources and all receivers within a continuous 3D medium, rather than just like at discrete points. And that again comes from the fact that we can take all the derivatives of the network analytically. Time to transition. Excellent.
Yeah, let me stop recording really quick.